Turbo machines. Chapter 12 deals with turbo machines, and these are mechanical devices composed of a rotor bound to numerous blades where fluid flows over the blades. There are two kinds: pumps, where energy is supplied to the fluid, and then there's also turbines, where energy is extracted from the fluid. Example of a pump would be something like a common household fan, and for a turbine, this would be a windmill. The flow rate of these fluids are classified into three categories. The first is axial flow, and this is where the flow follows an axis. And then there's radial flow, where the fluid flows around a radius. And a mixed flow contains both axial and radial flow components. With fluid flow comes energy transfer. And since our flow rates are going to be 3D and unsteady, we're going to make some assumptions to make our calculations a bit simpler. So first, we're going to assume that the fluid is perfectly guided by the plate. This means that the relative velocity, which is the velocity that someone would see if they were sitting directly on top of the blades, is going to be parallel to the length of the blade itself. And we're also going to assume that the blade speed at the entry point is equal to that at the exit point. And we define the blade speed to be the angular velocity times the radius of the turbo machine. These assumptions allow us to state that the absolute velocity, which is the velocity seen by an object directly across from the fan blades, is equal to the relative velocity plus the blade speed. Now, to define this flow rate in terms of velocity, we say that as the fluid is directly above the fan blade, the absolute velocity is equal to 0. And as it flows past the fan blade, if the fluid is being pushed by the blade itself, the device is a pump. But if the opposite occurs, and if the fluid pushes the blade, then the device is a turbine. We can also say that momentum transfer occurs because both torque and angular momentum are present within the system. And this is defined using the moment of momentum equation that relates both the work and the shaft torque present. And when we make the assumption that the flow is one-dimensional, we are able to derive the Euler turbo machine equation, which gives us the shaft torque in the system. This also tells us that a negative flow rate means flow is entering the system, and a positive flow rate means flow is leaving.
Centrifugal pump is one of the most common pump designs. It is used over 2/3 of pumping applications. The versatility of centrifugal pumps makes it the number one choice for displacing fluid in several industries such as agriculture, power generation plants, pharmaceutical, chemical, mining, and so on. We can break down centrifugal pump into three main components: impeller, casing, assembly of bearing, shaft, rotor. As impeller rotates, fluid is pushed radially outward in all directions, and a low pressure region is created at the center of the impeller. And while rotating, it imparts kinetic energy to the fluid. As fluid reaches the edge of the impeller, it gains a very high velocity, and fluid flows into the volute, the extended channel, and that's how the flow is formed. Pump curve is a graphical representation of performance characteristics of a pump. As we can see, fluid is plotted against x-axis, and head, efficiency, and brake horsepower are plotted against y-axis. Head is the amount of pressure differential generated by pump at any given flow rate. Efficiency is the ratio of power gained by fluid to shaft power driving the pump. Shaft power driving the pump basically called as brake horsepower. In the pump curve, we can see head developed at zero flow rate is called shut-off head. Efficiency is 0 at this point because there is no discharge, and brake horsepower dissipates at heat. It increases while flow rate increases. Efficiency is a function of flow rate, and it reaches a maximum value at a given flow rate, and this flow rate is called design or normal flow rate. Net positive suction head is a vital performance factor. It can be calculated with the given equation. NPSHR is the minimum amount of absolute pressure required at a pump suction head to keep the fluid in a liquid state. NPSHA is the actual pressure at a suction head on a particular system depending on parameters such as liquid boiling point, installation type. NPSHA value has to be higher or equal to the required value to operate the pump by preventing cavitation.
Dimensionless parameters and similarity laws. The characteristics of a pump are usually determined experimentally. These variables depend on the geometry, which can be represented by some characteristic diametrically, shown here as the dependent variable. A straightforward application of dimensional analysis leads to the dependent pattern. The power appearing in this dimensionless parameter is commonly based on the shaft brake horsepower, In terms of dimensionless parameter, the performance characters are expressed as these equations you see below. The last pi term in each of the equation is a form of the Reynolds number that represents the relative influence of viscous effect. When the pump flow involves high Reynolds number, as is usually the case, experience has shown that the effect of the Reynolds number can be neglected. Two pumps that operate at the same value of flow coefficient. Using the dimensionless parameter, the flow coefficient, we can see that these three equations provide a desirable relationship among a family of two pumps who have the same shape. If the two pumps from the family are operate at the same value of flow coefficient, they can be related. With pump scaling law, it is possible to experimentally determine the performance characteristic of one pump in the lab and use these data to predict the corresponding characteristic for other pumps that are within the same family that has different operating conditions. Showing here is a typical curve obtained for a centrifugal pump. This shows the result plotted in terms of the dimensionless coefficient C sub Q, C sub H, and C sub P, as well as efficiency. From these curves, the performance of different size geometric simulator pumps can be predicted, as can the effect of changing speed on the performance of the pump from which the curve were obtained. It is to be noted that the efficiency is related to the other coefficients through the relationship of the definition of the efficiency. Specific speed. Each family or class of pump has a particular range of values of specific speed associated with it. Suction specific speed. The suction-specific speed SS can be expressed as equation 12.45, a dimensionless number that is useful in determining the required operating condition on the suction side of the pump. As was true for the specific speed, and as the value of SS commonly used is for peak efficiency. In the United States, SSD is used, as you can see in equation 12.46. Here you will see the equation of a specific speed for a turbine. Flow and mixed flow pump. Axial flow pumps are often called propeller pump. Here you can see a schematic of an axial flow pump. Some axial flow pumps also have inlet guides to vanes upstream, while some are multi-stage. Axial flow pump usually have specific speed NSD in excess of 9,000. Very high specific speed pumps do not have starter vanes. To determine the characteristic of a centrifugal pump and an axial flow pump, this graph compares an axial flow versus a centrifugal flow pump by the typical head, power, and efficiency. At maximum efficiency, the two pumps are the same. As the flow rate decreases, the power input for the centrifugal pump falls to 180 horsepower at shutoff, while the axial flow pump increases to 520.
This brings us to our next topic, fans. A fan is a device that pumps gases and vapors. There are two types of fans. Centrifugal fans consist of radial flow, while propeller fans consist of mixed and axial flow. By solving for a specific speed, we can determine which fan to use. Centrifugal fans have a specific speed between 2,000 and 20,000, while propeller fans have a specific speed between 50,000 and 200,000. The associated equation is given here. It's the same as that for a pump, but a pressure term replaces the head term. Now we move on to turbines. A turbine is a device that extracts energy from a flowing fluid. The fluid exerts a torque on the rotor, which results in shaft work that is able to power generators. The first type of turbine are impulse turbines, which are categorized as having a negligible pressure drop in the blade passage, a major pressure drop at the nozzle, and a high head and a low flow rate. Examples of impulse turbines are the Pelton wheel and axial flow impulse turbines. Both have the characteristic that the magnitude of the relative velocity does not change, but direction does, which induces a torque and results in work output. To calculate shaft work in a Pelton wheel, we need to know the tangential components of the absolute velocities of the inlet and outlet. From the figures, we can calculate the inlet, which is v theta 1, and the outlet, which is v theta 2. By assuming that the work caused by velocity and the inlet and outlet are equal, we can set both equations equal to each other and get this. From here, we can solve for torque, which is just the velocity difference multiplied by the mass flow rate and radius. Since speed equals angular velocity and radius, we can solve for shaft work, which is torque times angular velocity, yielding this equation. We can solve for V1 using the energy equation that we've done before, and all other constants are listed. We can also calculate the shaft work for an axial flow turbine. It is important to note that the only torque on the control volume is the shaft torque. Therefore, the radius is equal to half the radius of the blade tip and the blade base combined. The resulting shaft energy is given by this equation. From this, we can solve for shaft work given here. The second kind of turbines are reaction turbines, which are categorized as having pressure drops at both the nozzle and vane, a low head, and a high flow rate. The vanes accelerate the flow and can be adjusted to produce maximum output. The two types of reaction turbines are Francis and Kaplan turbines. Both have a tangential component of velocity, with the Francis turbine having radial and mixed flow, and Kaplan turbine having axial flow, which is the most efficient type of flow. We can calculate turbine efficiency as being the inverse of pump efficiency due to them being opposite. We can also make an alternate version by setting some dimensionless parameters for flow, head, and power given here, and the subsequent efficiency result would be this. We can calculate the specific speed for a turbine with this equation. Note that the flow rate gets replaced with shaft work because the flow rate is a dependent variable for turbines. We can then use the calculated specific speed along with this graph to determine which turbine would fit best.
Thank you for watching.